Hello everyone. In today's lecture, we are going to learn about what's called the goodness of fit test, which is performed on categorical or qualitative data using a chi-squared distribution. Now, as you know, categorical or qualitative data comes to us in the form of names and not numbers. And therefore, measures like the mean or the standard deviation do not apply to categorical data. The only measure that would apply is the frequency distribution or the number of occurrences of a certain observation. So in this lecture, we are going to learn about the goodness of fit test, the purpose of it, and then the process of performing a goodness of fit test using an example. We will first learn what the chi-squared goodness of fit test is and its purpose. It is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. In other words, it is a comparative study. It compares the frequency distribution of a certain variable obtained from a recent study with the distribution of the same variable in the past, perhaps 20 years back. So, for example, if we want to know whether the frequency of occurrence of heart disease has stayed the same today as it was 20 years back, or whether it has changed due to medical advancement, perhaps it has gone down, or perhaps it has gone up due to lifestyle changes. If we want to understand the frequency of occurrence or the frequency distribution of heart disease today versus what it was 20 years back, then the goodness of fit test can be applied for that. So it says here the chi-squared goodness of fit test determines if the observed frequencies of a variable at a particular time has changed from that in the past based on expected frequencies. So these are the two terms that we will be using in our study on goodness of fit test. Observed frequencies refer to the frequencies of a variable done from a recent study, and the expected frequencies refer to the frequencies of the same variable from the past. All right? Now, before we go into the step-by-step procedure of performing a goodness of fit test, let's spend some time on understanding how we can calculate the expected frequency. Now, previously we said that we will talk about two terms. One was the observed frequency, the other was the expected frequency. Observed frequency would apply to recent data obtained from a recent study. So that would be actual data, actual frequency values. Expected frequencies, on the other hand, refer to past frequencies, right? So will be given to us in the form of relative frequency values, in other words, proportions or probabilities. Now, relative frequencies and probabilities, those two terms are used often interchangeably. So the past frequencies will be in the form of relative frequencies and not actual frequency values. All right, so we have to calculate the expected frequencies denoted by the letter E using a simple formula, which is N times P, where N is the sample size and P is the relative frequency or the probability. The past information will be given to us for the different variables in the form of relative frequencies. We will have to convert that to frequency values using this particular formula, N times P. So this is going to be the first step in the calculation of a test statistic chi-squared value. We first have to list all our observed frequencies and then calculate all our expected frequencies, and then we have to take the difference between the two and go through the entire process based on the chi-squared formula to come up with a test statistic chi-squared value. Let's go over the chi-squared formula that we will be using to find the test statistic for our goodness of fit test. This is how it goes. Chi-squared equals sigma, or the summation of, within brackets, O minus E whole square divided by E. Now O stands for observed frequencies, E stands for expected frequencies. Observed frequencies are actual frequency data that were obtained from the recent study. So those will be actual frequency data. Expected frequencies have to be calculated because the past data will be given to you in the form of relative frequencies or proportions. To convert them to frequency values, you will need to use the total sample size and multiply each of the proportions that apply to the different types of variables and multiply them. E equals N times P that we discussed previously. We will be using that formula to find the different expected frequency values, and then once we have all the expected frequency values, since we are doing a comparison between the observed frequencies and the expected frequencies, we have to find the difference between the two. We have to square them up and then divide by each of the expected frequencies, and at the end we have to sum them all up. Now normally I work this entire process through a table. It's much cleaner and easier to work through a table, and that's what I'm going to demonstrate when we go through the step-by-step procedure. Now another important thing that we have to remember is how we calculate the degrees of freedom. The degrees of freedom for a chi-squared goodness of fit test is this: 1 less than the number of possible values for the variable under consideration. So again, we are dealing with qualitative or categorical data. Therefore, our values will be names and not numbers. Therefore, to find the degrees of freedom, we will take the number of different types of the variable, that is the number of the different categories of the variable, and subtract 1 from it. So the formula to find the degrees of freedom is C minus 1, where C is the number of categories of the variable that we are dealing with. All right? So let's go through the steps of performing the goodness of fit test. We'll start with the assumptions. The first one says all expected frequencies are greater or equal to 1. We will be calculating our expected frequencies using the formula N times P. However, once we have the values, we have to make sure that there are no expected frequencies equal to 0. They have to be 1 or more than 1. Now, at most, 20% of the expected frequencies are less than 5. So if we have any expected frequency values that are less than 5, that means between 1 and 4 inclusive, then that should not be more than 20% of all the expected frequencies. And third, the data has to be from a simple random sample. Step 1 is stating our hypothesis. The way we state our null hypothesis, which is the status quo hypothesis, will say that there is no change in the distribution. The variable has the specified distribution. Alternate hypothesis will say the variable does not have the specified distribution. So null hypothesis is going to state that there has been no change in the distribution of today's data from that of the past. All right, it matches with the distribution from the past. An alternate hypothesis will say that the distribution from the recent study has changed from what it was in the past. All right. Step 2 is to decide on the significance level alpha. Step 3 is to come up with the test statistic value using the formula for chi-squared. And as I said before, we will work through it using a table. So these are the first 3 steps of performing the chi-squared goodness of fit test. And then we will go through the next 3 steps of using the different approaches, coming to a decision, and then, of course, interpreting the results. So step 4 is to use the critical value approach or the p-value approach. Now keep in mind that we are using the chi-squared distribution. So when you draw your curve, make sure that it is a chi-squared curve and not a normal curve. The chi-squared curve is anchored at 0. The smallest value that a chi-squared test statistic can have is 0. All right, so this is how it looks like. It's always going to be a right tail test because it is a right skewed curve. So reject region is always going to fall on the right hand side. Do not reject region on the left hand side. The DF, which you will need to calculate the critical value or the cutoff between the reject and the do not reject regions, is going to be C minus 1, the number of categories, minus 1, where C is the number of possible values for the variable. If we are using the p-value approach, again, you have to draw your chi-squared curve, and then you have to show where your test statistic value falls on the curve, and then find the area to the right of that value of the test statistic value to obtain the p-value. All right. And then for the critical value, if your test statistic value falls in the reject region, you reject the null hypothesis, otherwise you don't. For the p-value approach, if the p-value is less or equal to the alpha value or the significance level at which you are testing, then you reject the null hypothesis, otherwise you don't. And finally, you interpret the results in step 6 in terms of the problem that you are working with. You have to interpret it in the context of the problem that you're dealing with, right? Now we will be going through the step-by-step procedure of performing a goodness of fit test using an example. So we have the example up here. We are going to first go through it, try to understand what the problem is that we have to test here, and then identify the 2 types of data involved in studies of goodness of fit tests, of the frequency data versus the relative frequency data, the recent data versus the past data, and so on. So let's spend some time on just understanding the problem and the data given to us. It's on violent crimes, and apparently it seems that they are comparing the incidence or the occurrence of certain types of violent crimes obtained from a recent study with the frequency of occurrence that used to be in the past. The FBI compiles data on crimes and crime rates. The table below gives the relative frequency distribution for reported violent crimes in 2010. So that is the data over here. A simple random sample of 500 violent crime reports from 2019, which is this data in green, yielded the frequency distribution shown in table below. Suppose that we use the 2 sets of data to decide whether the 2019 distribution of crimes changed from the 2010 distribution. All right, so that is what the study is about. We are comparing the distribution of the different types of crime from 2019 with the data from 2010, right? So this is the more recent data, and just note that they have given to us the frequency values for each of these different types of violent crimes. Whereas for the 2010 data, which is the past data, they've given us the relative frequency values, right? So these numbers here are relative frequency values. Now this could also have been given to us in percentage. You would need to convert those percentage values to relative frequencies when we go about calculating expected frequencies and so on. But relative frequencies, percentages, and probabilities are often used interchangeably. However, for percentages, you have to change the relative frequency decimal values to percentages by multiplying by 100, whereas relative frequencies and probabilities are always decimal values between 0 and 1 included. All right? Now that we understand the problem and the related data, let's try to answer some questions here. The first one is, what is the variable and its possible values? Now, the variable for this particular problem is types of violent crimes. The question is comparing the incidence or the frequency of violent crimes. So the variable is violent crimes or types of violent crimes. And then what are the possible values? The possible values are the 4 categories of violent crimes that we are studying. So at this point, I'm going to pull up the table of data. Here we had the data given to us. The 4 possible values that the variable violent crime could take are murder, rape, robbery, and assault. So these are the categories of the variable. All right, and there are 4 of them. So you have to state the possible values are murder, rape, robbery, and assault. Keep in mind that we are working with categorical or qualitative data which comes to us in the form of names. So these possible values will not be numbers. They will be names, the types of violent crimes. Please do not write the frequency numbers for the possible values. It's the categories of the variable that we are working with. All right. Now the next question says state the hypothesis. The null hypothesis, which is the status quo hypothesis, will say that there's no change in the distribution. Today's distribution is the same as that in the past, and you have to, of course, state it in context of the problem. So here we have the null hypothesis as year 2019 crime distribution is the same as that in 2010. And your hypothesis, because again we are working with categorical data, there's no mu or p or any quantitative measures, you will have to state it in the form of a sentence relevant to the problem that we are dealing with. So null hypothesis states year 2019 crime distribution is the same as in 2010, whereas alternate hypothesis will state that no, it has changed. So year 2019 crime distribution is different from that in 2010. All right. Now, before going into the calculations of the test statistic, let's spend a little bit of time understanding the basic idea and the approach of carrying out this test. The whole idea is to compare the observed frequencies from the recent study with the expected frequencies obtained from the past, and then come to a conclusion whether the frequency distribution has changed or if it is the same. So we are making a comparison, and then if the observed and expected frequencies match fairly well, if they are close enough, then we conclude that they did not change, the frequency distribution did not change. We do not reject the null hypothesis. Now the next question is how we determine what the expected frequencies should be, because we will not be given the expected frequencies. Instead, we will be given the relative frequencies from the past. Either we will be given the relative frequencies or the percentages. So if you are given the percentages, make sure you convert them into relative frequencies by dividing by 100, and then you have to perform the computation of the expected frequencies using those proportion values and multiplying them by the total sample size. And then secondly, we have to decide if they match or not, or if they are different. And for that, we will be using our test statistic formula to decide on that by comparing the observed and expected frequencies and how much they are disparate from each other, how much they are off from each other. So at this point, I'm going to first perform the calculation of the expected frequencies E. Now, like I said before, I'm going to use a table because it's much cleaner and easier to work with, starting with calculation of the expected frequencies, and then we will extend that to calculating the chi-squared values. All right, so I'm going to pull up my data. So here we had the data that was provided to us. This orange data is the 2010 data, which is all relative frequencies, and the green data is the recent data, which is frequency values, correct? So we start our table. The first column is just listing the type of violent crime, in other words, the different categories of the variable that we are dealing with. So in this case, we were dealing with the variable violent crime, and the 4 categories that were given to us are these: murder, rape, robbery, and assault, correct? And then on the next column, you list all the relative frequency values given for the past data and indicate that with P. So these are also values that will be given to us, that will be provided to us. So just copy it from your data table. These are all relative frequency values. Now, if by chance you are given these numbers in the form of percentages instead of relative frequency, you have to convert them to relative frequency value. So if instead of 0.012 you were given 1.2%, you would have to convert the 1.2% to a decimal value and write it on this table. All right? Do not use 1.2. It has to be converted to a decimal value, in other words. For the next column, the third column, these values will also be given to you. These are the observed frequencies, and these are the frequency values, correct? So that's the third column. So the first 3 columns were pretty much given to us. No calculation was needed. The fourth column is where we find our expected frequency using the formula E equals N times P. Correct? E is the expected frequency, N is the sample size, and P are all these proportion values of the relative frequencies. Correct? So what we are doing is multiplying each of these P values with N. What is N? N is the sum total of all the frequency values from 2019 in this case. So all the observed frequency values. Again, you are multiplying by N, not by these individual frequencies. Essentially, you are multiplying 0.012 with 500. So let me just write that. We are multiplying 0.012 by 500 will give us 6.0. Likewise, 0.068 multiplied by N, which is 500. So all of these proportion values are getting multiplied by N, and then you write that value in the expected frequency column. So the expected frequency column for murder will have a value of 6. The next one will have 34. Robbery was 147.5 and assault was 312.5. These were the incidents or the expected frequencies based on the proportions from 2010 distribution. All right. Now, once we have calculated all the expected frequency values for the different categories, we can go ahead and extend the table to find our chi-squared test statistic value. And we are going to go again step by step. We have to add a few more columns. So what I'm going to do here is first write the formula for the chi-squared test statistic value. So it's going to be sigma, then O minus E whole squared divided by E. That's the formula to calculate the chi-squared value. And I'm going to take the different parts of this formula and calculate it over the different columns. All right. So the first one is to compare O and E. And we do that by taking their difference. So essentially in this column, we are performing this part of the formula, which is just O minus E, whatever is inside the brackets. So to find the difference, just take your observed frequency values for each category and from it subtract the expected frequency value and note it down in the difference column. So 3 minus 6.0 is negative 3.0. 36 minus 34.0 is 2.0. Once we calculate all the differences, we will go on to the next column, which is squaring all the differences. So minus 3.0 squared is 9.0. 2.0 squared is 4.00 and so on. All right. And then the final column is to take all the squared difference values and divide them by their expected frequencies. Therefore, 9 divided by 6 gives us 1.5. 4 divided by 34 is 0.118. So that's the final column, which is O minus E squared divided by E. So in this last column, we are essentially dividing this O minus E whole squared from the previous column with the corresponding expected frequency values for each category. And finally, we will sum up all the values in this last column, and that is going to give us our test statistic value of 6.529. Right? Now at this point, we are going to complete the different steps of the goodness of fit test. We'll start by checking the assumptions. The first assumption over here is, are all the expected frequencies greater or equal to 5? So we are looking for the expected frequency values, which we calculated using that N times P formula. I'm going to bring up that table, that list, and check whether there are any expected frequencies less than 5. All right, so here is our table. We have to look down the column for expected frequencies and we see 6, 34, 147.5 and 312.5. They are all greater than 5, so that condition has been met. There was another condition that the data should come from a simple random sample, and the question here says it's simple random sample of 500 violent crime reports. So that condition has been met as well. Now there was another condition which is applicable only if there are any expected frequencies less than 5. If there are any expected frequencies less than 5, then we have to make sure that at most 20% of the total expected frequency could be less than 5. But it's not applicable in this case because all our E values are greater or equal to 5. All right. Now the next step is to state the null and alternative hypothesis. So I'm going to just get rid of the table at this point and look at how we state the null hypothesis. The null hypothesis is always going to state that there's no change in the distribution of crime in 2019 from that of 2010. Right? So I'm going to take a pause and write that down, and then we'll talk about the alternate hypothesis. So I've written here, for the null hypothesis, the distribution of violent crimes in 2019 is the same as that in 2010. As far as the alternative hypothesis is concerned, it's going to say that the distribution of violent crimes in 2019 has changed from that in 2010, or is not the same as that in 2010. So here we go for the alternative hypothesis. The statement is the distribution of violent crimes in 2019 has changed from that in 2010. The next step is to decide on the significance level alpha. Now we've been asked to perform this test at the 5% significance level. The alpha value is going to be the decimal version of 5%. So just divide 5 by 100 and that should give us a value of 0.05, and that is going to be our alpha value. Now the third step in the process is to find the test statistic using the chi-squared formula for goodness of fit test, and we've already performed the calculations through the table a few slides back. So all I'm going to do at this point is pull up that table and make a note of the test statistic, right? So here is the table that we worked through. The chi-squared value was 6.529, which we obtained after summing up all the values in the last column, all the chi-squared subtotal values. These are the subtotal values for the individual categories. When we sum them up, we got a chi-squared value of 6.529, and that is going to be our test statistic value, 6.529, which we will use to perform the test. Now at this point, we are going to perform the test using the critical value approach first. And in the critical value approach, we have to start by bringing up a curve, a chi-squared curve in this case, and then showing the reject and the do not reject regions and finding the critical value, the cutoff between the reject and the do not reject regions, correct? Now the chi-squared curve is a right skewed curve, and the hypothesis test therefore is always going to be right tail test. Now in any right tail test, the reject region will be located to the right of the curve. All right, so all chi-squared curves are right skewed curves. Keep that in mind. Therefore, all hypothesis tests will also be right tail tests. So I'm going to show my reject region on the right hand side, reject, and then the do not reject on the left hand side, and the area corresponding to the reject region is going to be my alpha value 0.05. So I have to go ahead and find the critical value or the cutoff point on the horizontal line between the reject and the do not reject region. It's going to be a chi-squared value corresponding to 0.05 alpha, but we have to consider what the DF is, right? The degrees of freedom. Now the formula to calculate the degrees of freedom is C minus 1, where C is the number of categories involved, correct? So there were 4 categories of violent crimes. So our DF value is going to be DF equals C was 4. So 4 minus 1 is going to be 3. So our DF in finding the critical value is going to be 3. So at this point, I'm going to pull up the chi-squared distribution table to come up with a value of the cutoff, correct? So let me just do that here. So here's our table. I'm going to go down the degrees of freedom column on the left hand side until I get to 3, which is our degrees of freedom for this exercise, and then go all the way across until you come to 0.05 for the alpha value, this topmost row, 0.05, and the point of intersection between the 3 the row 3 and column 0.05 is 7.815, and that is going to be our critical value. So I'm going to write that out. CV critical value is chi-squared of 0.05 with DF equals 3, and that's a value of 7.815. I'm going to write that over here too on the diagram, 7.815. And then what was our test statistic value? The test statistic value, which is chi-squared sub 0, was 6.529 that we calculated from our table. And where does it fall on the curve? It falls to the left. It's less than 7.815, correct? So 6.529, and let me write this down at the same time, is less than the critical value, which is 7.815. So it falls in the do not reject region, falls in do not reject region. Therefore, we are going to not reject the null hypothesis, correct? The decision is going to be to not reject the null hypothesis. Do not reject the null hypothesis. So let's perform the test using the p-value approach at this point. In the p-value approach, there's no reject, do not reject regions. We start with our test statistic value, which I've written down here. It was 6.529. I have the curve on this side, and I'm going to represent 6.529 on the curve and find the area to its right, which will give us our p, or the probability value, right? So let me just mark that 6.529. somewhere on the curve here, 6.529. I'm going to extend the line up, and this area to the right of it is going to be our p-value, right? So this is going to be our p-value. Now, when I used my calculator to find the p-value, right, so we are essentially finding the p-value of chi-squared sub 0 of 6.529 with df equals 3, correct? Degrees of freedom was equal to 3 using the formula c minus 1, where c was equal to 4. And if you use a statistical tool, you can get the exact p-value, and in this case it's 0.089 rounded to the third decimal place. If you're using the table, you will be estimating the p-value, which I will show you, but the exact p-value is 0.089. The next step is to compare p with alpha, correct? So the question we are asking is p less than alpha? If it is, then we will reject the null hypothesis, otherwise not. So p was 0.089. The alpha value is 0.05, which is our significance level, and that is greater, correct? 0.089 is greater than 0.05. Therefore, do not reject the null hypothesis is going to be our decision, which matches with what we found using the critical value approach. Now, I'm going to pull up the table and just show you the estimation of p from the table. So to estimate the p-value from the table, you have to take your test statistic value 6.529 and go along the row for the degrees of freedom, which in our case is 3, and see where it would fall in this list. This is a truncated chi-squared table. So you start comparing with each of these values from left to right, and we see that 6.529 would fall to the right of 6.251, considering that all these values are increasing from left to right. So let's write that 6.529 would fall between 6.251 and 7.815, and then we have to go up and see that it's going to be a value in between 0.10 and 0.05. In other words, it's going to be a value greater than 0.05 but less than 0.10. All right, so let's write it like this. The estimated P is going to be 0.05 is less than whatever the P value is. If we are using the table, then we of course don't know what the exact P value is, and P is less than 0.10. So this tells us that P is greater than 0.05. Therefore, we should not reject the null hypothesis, right? Finally, we will formally state our decision, which was do not reject the null hypothesis. Now, the null hypothesis had stated that there was no change in the distribution between 2019 and 2010. Correct? Now, when we make our interpretation, that should be in agreement with the decision. So the way we interpret this is that at the 5% significance level, always qualify your interpretation with the significance level at which the test was performed. At the 5% significance level, the data do not provide sufficient evidence. So if you did not reject the null hypothesis, then your data was not strong enough, not sufficient enough, and therefore do not provide sufficient evidence to conclude that the 2019 distribution of violent crimes changed from that in 2010. All right?